Hey everyone, welcome back to our channel. Today we're going to talk about the Physics 9702, the CIE A-Level Physics Paper 4, variant 4.1, which is identical to 4.3, and the session in the exam year that we're going to talk about is October-November 2024. And this is for the preparation of May-June 25 exams. Now, before we dive into this exam, we wanted to show you something, which is this grade booster pack that we have compiled for AA2, which is the A-level content. That includes frequently examined questions. We have been uploading them for about 3 or 4 years now, but every year it gets polished a little bit better. This year we have furnished it much better this time. So what's new this year, are the syllabus points and the questions relevant to those syllabus points are aligned. The answers, as before, they are marking scheme aligned, and one more new thing over here are the years listed at the right hand column. So you might see some questions with a lot of years listed over here. Obviously the variants are not listed over here, but the year and the exam sessions are. This is enough to show you that these are important derivations. Oh, sorry, important questions. Speaking of derivations, we have a separate doc for derivations. All the important derivations that are listed in the syllabus and the very frequently uh, examined derivations in the past papers, we have listed them over here. Especially this one we will be seeing this in this paper also. Third thing, which is definitions and formulae. So like the basic rundown of the basic terms, not basic, all the terms, all the important terms, any important formulae. And last but not the least, the graphs. Graphs, we know every student struggles with the field and the potential graphs of gravitational fields chapter and the electric field chapter. So we have got you covered over there. So hopefully when you go through these, you will get a better understanding of the graphs and everything. And this, again, is all neatly packed in the grade booster pack that we have on our Patreon. We will put this link on this video. All right, starting with this paper. So let's see the first question. State Newton's law of gravitation. Now, just to show you that I just actually showed you over there, but just to show you that these type of questions, which are very frequently occurring, we have listed them over here and answered that for you with the proper model answers. Now, writing over here. So, okay, I wanted to show you one thing. So, the definition is easy, but there's a huge assumption over here that is often neglected by the students, and that is the assumption of the point mass. So gravitational force is directly proportional to the product of the masses of the two objects, and inversely proportional to the square of separation between their centers, because we are assuming that those two objects are point masses. So either we include a phrase about the two point masses, or we specify that the separation is between their centers. So we can say that the gravitational force between any two point masses is proportional to product of their masses and inversely proportional to square of their separation. Simple. So we can write the point mass thing over here. Now, let's see. A planet may be considered as a uniform sphere. A satellite is in circular orbit of period t and around the planet at a height h above the surface. So this keyword over here is very important. So above the surface means that this is radius plus the height h. That means that the small r that we use in the g/m/r squared, that is radius plus height. Radius of the planet plus height, h. Figure 1.1 shows the variation of h with t raised to power 2 over 3. By reference to forces, explain why the orbit of the satellite is circular. Okay, now had the question been just simply explain why the orbit of the satellite is circular, we just had to explain that the centripetal force is provided by the gravitational force acting on the satellite towards the center of the planet. However, they're asking for by reference to forces, so that means we need to be a little bit more specific about this. So what's more specific than this is that the gravitational force acting is perpendicular to the direction of motion, which actually qualifies for the circular motion. So we can say that the, all right, so gravitational force acting on satellite directed towards center of the planet remains perpendicular to satellite's velocity. Therefore, providing the centripetal force. That's it. That's all we have to say. All right. Use Newton's law of gravitation to show that h and t are related by this. So this form over here, this is very similar to, let us show you, this one, the Kepler's law. So we have this definition, we have this derivation over here, and the key thing is that the gravitational force is equal to the centripetal force, which we have already written in the previous part. So that's already a given over here. So we can start out by saying that the gravitational force is equal to centripetal force. So G-M-M over R squared equals to a, yes, mr. We have formed mr omega squared, centripetal force, right? Omega is 2 pi over t. So we can just straight away go with 4 pi squared over t squared. Now when we rearrange this equation, first we cancel out the m of the satellite. This becomes r cubed gm over 4 pi squared t squared. Now we specify that r is equal to radius. They have given in this b of planet plus height h. So secondly, mass m is m is mass a of planet. So therefore this becomes h plus b cubed equals to GA over 4 pi squared t squared. That's it. That's all we have to do for now. Use the gradient and intercept of the line in figure 1.1 to determine the values for A and B. Alright, so before we actually go with that, we need to convert this into the straight line equation that we had. So remember in the graph, we had t raised to power 2 over 3 against h. So that means we need a y is equal to mx plus c form where h is our x. So first off, what we do, we make this we make t squared the subject instead. So 4 pi squared over G A h plus b whole cube. The next step would be to take the cube root on both sides. So we will get t raised to power 2 over 3. This part 4 pi squared over G A, this becomes cube root h plus, since this part cancels out the powers 3, 1 over 3, you can study the indices laws from maths, times by b. So this is our y is equal to mx plus c. So this is y, this is m, this is your x, and this is your c. Entire thing is your c. Now, first off, obviously the y-intercept has two unknowns, so we can't actually start with that. But we can start out with gradient because we have only one unknown in this quantity. So we go back to the graph and find out any 2 points where we can take the gradient for. So first off, we need to know how the y-axis resolution works. So if 400 is divided into 10 markings, that means each mark represents 40. So this would be 400 minus 40, 360. So this point is 0, 360. And we need just one more point. So let's take this one. This one also, okay. I think we can take this one. Okay, yes. So 11, 1200. And the height is actually in 10 raised to power 6. So we have to be very careful about this. So gradient. So gradient 1200 minus 360 over 11, 10 raised to power 6 is equal to the cube root of 4 pi squared over GA, like this. So first off, let's find out the left-hand side. 1200 minus 360 divided by 11 times by 10 raised to power 6. We need this in the standard form, so, oh, sorry. So 7.63, basically, sorry, no, 6, 10 raised to power minus 5 equals to 4 pi squared over GA. Now, to get rid of the cube root, we take the cube on both sides. We take the cube. This becomes this. So we have 4 pi squared over GA equals to 4.5453 07 times by 10 raised to power minus 13. Now we cross multiply to find out A. So A would be 4 pi squared over G is 6.67 10 raised to power minus 11 times by this value 4.45307 10 raised to power minus 13. So times by 6.67 times by 10 raised to power minus 11, and then 4 pi squared divided by answer. We get this value, which is 1.329, so 1.33 or 1.3 10 raised to power 24 kgs. Now we need to find out B. For B, we need to look at the y-intercept. We already have the y-intercept, 0, 360. So y-intercept, if you see, is basically just the gradient times by B. So B would be y-intercept divided by the gradient. So y-intercept is just 360 divided by the gradient, that was 7.636 10 raised to power minus 5. Okay, let's see if we can go back and get the original value. So never mind, we can just plug it over here. So 360 divided by 7.6363 10 raised to power minus 5. So we get 4.7 10 raised to power 6. This is going to be in meters. So over here we will write 1.3 10 raised to power 24 kgs and 4.7 10 raised to power 6 meters. SI units, basically. All right, good. Let's move on to the next question. So define specific heat capacity. So again, you can find the definition in the docs, but let's write over here. So amount of heat or thermal energy required. So amount of thermal energy required to change, sorry, you can rewrite required, gained or lost also. So gained or lost to change the temperature of a unit mass of a substance by 1 unit temperature. You could also say by 1 degree Celsius or Kelvin. Two solid blocks, X and Y, are made from different metals. The blocks have different initial temperatures. Block Y is initially at room temperature. Blocks are placed in direct thermal contact with each other at time t is equal to 0, shows the variation T of the temperatures of two blocks. Thermal contact, as the word already suggests, that means heat exchange is allowed. State three conclusions that may be drawn from figure 2.1. The conclusions may be qualitative or quantitative. Okay, all right. So let's see the points that we can actually talk about. So first off, this final temperature is where the thermal equilibrium is happening. So this is very obvious that they have the final same temperature. So let's mark that line. Okay. And let's see the numbers over here. So if 25 is divided over 10 markings, so each point represents 2.5. So that means this is, so 2 points will represent 5. So 30, 35, and 40. Similarly, this one 80, 85. So the change in temperature over here, this one is 15, and this one is 45. Sorry, this one is gaining, so I'll use an up arrow. Okay. Oh, sorry. All right. Right. Okay. I hope. Not bad. Right. So this is simple an observation. This is not a conclusion yet. So what can we deduce from this is the fact about the thermal capacity or heat capacity. So we know heat capacity is based, or the energy equation mc delta theta, uh, q is equal to mc delta theta, can also be written as q is equal to c delta theta, which is the heat capacity, not the specific heat capacity or thermal capacity. So since energy lost is energy gained over here because there's a thermal contact over here, so Cx delta theta x is equal to Cy delta theta y. This is not q, this is theta. So the heat capacity relationship is theta y over theta x. So theta y is basically just 15, and this is 45, so this is 1/3. So we can cross multiply to see that heat capacity of y is 3 times the heat capacity of x. Because it's taking more, it requires more energy to change the temperature by 1 degree. So this is the first observation that we can make. So heat capacity of y is 3 times larger than that of x because of because drop in temperature for drop in temperature of x is 3 times gain of x. All right. Second most obvious thing is the thermal equilibrium because they both have the final same temperature. Both objects attain thermal equilibrium as they have a common final temperature. And since there is no temperature change further happening, whether increase or decrease, that means that there is no heat exchange with the surroundings. So no heat exchange with surroundings as final temperature remains constant. That's it. All right. The ratio mass of block Y is equal mass of block Y to mass of block X is equal to 1.3. The metal in block Y has a specific heat capacity of 901. So determine the heat capacity of the metal in block X. Okay, so we saw this over here also. We are going to use a similar version of this uh, equation, but with the specific heat capacity instead. So heat lost by X is equal to heat gained by Y. So mx small cx delta theta x equals to my cy delta theta y. Now, since we are interested in cx, we will take away everything on the other side, but we have the ratio of masses and ratio of temperatures, so arranging them is slightly easier. Mass m over mass x delta theta y over delta theta x times by cy. So we know the ratio of masses is 1.3. Temperature change of y over temperature change of x is 1 over 3. And specific heat capacity of y, 901. So straightforward calculation, 1.3 times by 901 divided by 3. This is 390, you could say. So 390. That's it. All right. Question number 3. State what is meant by Avogadro's constant. So very simple definition. That is the number of particles in 1 mole of a substance. You could also say number of particles per unit amount of substance. State the relationship between Avogadro constant Na, molar gas constant R, and the Boltzmann constant K. This is straightforward. We know this. That is R over Ma. Two samples X and Y of ideal gases are both at thermodynamic temperature T. Sample X has volume V and consists of n molecules, each of mass m. Sample Y has a volume 2V, consists of 2n molecules, each of mass 2m. Complete table 3.1 by giving expressions in terms of sum or all of nmtv and the constants in A2 for the quantities indicated. Okay, so we know that ideal gases obey this PV is equal to NKT or nRT rule. So for pressure, NKT over V, just simply rearranging this equation. We can have an alternate of this one also. But since small n, which is the number of moles, is not included in these quantities, we have to rewrite n. N is number of molecules over Avogadro's constant. So if we replace k, we will have n RT over Na times by V. For sample Y, we have twice the volume, twice the number of molecules, twice the mass. So this 2n over here, this 2v over here brings us back to nkt over v, or nrt over na times by v. Amount of substance is basically this, what we just wrote over here, n over na. Over here, it's twice the number of molecules, so 2n over na. Mean squared speed. Mean squared speed is coming from the translational kinetic energy, which is half mc squared over 3 by 2 kt. So cancel out the 2's, take away the m on the other side. You have 3 kt over m. Now, you could replace out k again over here. So you could say 3RT over m times by NA. Again, that's up to you. It's unnecessary, but you can still do that. Similarly, we have twice the mass over here, so we can go 3 over 2 KT divided by m. And similarly, 3 over 2 RT over 2mNA. Okay, internal energy. So internal energy of ideal gases depends on just the sum of kinetic energies of all the particles. So since we are saying that or averagely it is the same, since we're talking about the average, the same for the same reason, we will multiply by n on both sides. So 3 by 2 nkt, okay? Or again, you could do the same thing we did over here. So 3 nrt over 2 na. For the sample y, we have twice the amount of molecules. So 2 and 2 get cancelled. So 3 nkt or 3 nrt over na. And that's your this. All right. So let's see the next question. The temperature of the sample is now varied. On figure 3.1, sketch the variation with thermodynamic temperature of the root mean squared speed of the molecules of the gas. Okay, so we have this graph also over here for your convenience. This one, the second one, basically on the right side. So this graph is due to the square root over here. So let us explain what is going on. So we have half mc squared equals to 3 by 2 kt, and then obviously we take away the half and take away the mass on the other side, we get this. This is mean squared speed. When we take the square root, we get the RMS speed. So that means the square root we will have is 3 kt over m. So CRMS basically is proportional to the square root of t. So square root graph rises like this, but after that it increases and it goes in a decreasing gradient like this, and that's it. All right, moving on to the next question. State what is meant by a simple harmonic motion. So the defining equation of the simple harmonic motion we already know is a minus omega squared x, which means acceleration is proportional to displacement from a fixed point and is always directed towards it. So a motion where acceleration, acceleration is proportional to displacement from a fixed point and is always directed towards it. That's it. A block is suspended from a spring as shown. The block is pulled down and released at time t is equal to 0. It then oscillates vertically with simple harmonic motion. Figure 4.2 shows the variation of the velocity of the block with height h of the base of the block above the floor. So basically, it's not the displacement, it's height h and the displacement. All right. Determine the amplitude in centimeter of the oscillation. So just to like show you where this, how this graph looks familiar, is because this is based on this graph. Based on, but obviously not the same thing. Because x over in this graph represents the displacement. The extreme right and the left points indicate the maximum amplitude, and the vertically highest and lowest point, w omega, omega x naught negative, they represent the maximum velocity. So that's exactly what we just need to extract over here. So for amplitude, we need to know the maximum and the minimum heights, and then subtract them, divide by 2, you will have the amplitude. So let's see. Uh, this is 1, this is 3, so this is 3.5. This would be 9, and this is then 9.5. So amplitude is easy to figure out now. 9.5 minus 3.5 divided by 2. So 9.5 minus 3.5 divided by 2, it's just 3 centimeter. Show that the angular frequency of oscillations is 3.2 radians per second. Okay, so highest velocity is omega x naught. So that is, 6, 7, 8, 9, and 9.5. Okay. So omega x naught is 9.5. So omega is 9.5 over x naught is just 3. And notice that we are dealing in centimeters over here. So this is velocity centimeter per second. Height is also in centimeters. So the units are taken care of. So 9.5, divided by 3, that is 3.2, roughly 3.166 recurring, basically. So that is approximately equal to 3.2 radians per second. Now, calculate the period t of oscillations. This is straightforward because we know that omega is basically 2 pi over t. So therefore, t would be 2 pi over omega. So 2 pi over answer is 1.984. So if 1.98, roughly approximately 2 seconds over here. All right. Had we done the 2 pi by 3.2 over here, so that is also almost the same thing. Okay, all right. On figure 4.3, sketch the variation of height with time. So previously it was height with velocity, now we need height with time. So we know what the height highest height is because that is the mean position. We need to know what the mean position is. So this is 3.5 plus 3. The mean position is actually sorry 6.5. So this is your mean position 6.5 over here. Okay. However, it is pulled down and released at time t is equal to 0. So it is pulled down, so that means the height will be at 3.5. All right. So that is the 3.5. So 3.5 and 9.5 we need to find over this. So again, we need to know what the resolution is. 2.5 divided by 10, that means 0.25. So to find 3.5 divided by 0.25, we need 14. So 14 means this is 10 and this is 4. This is 3.5, and for 9.5 divided by 0.25, you need 38. So 10, 20, 30, and this is your 9.5. So just to, be good about this, let's make the maximum and minimum lines this, and over the 9.5, like this. Okay. Now we need, now we need the uh, graph. So we'll make the graph with a different color and slightly thicker line. So we know that at t is equal to 0, it's 3.5. At 1, it's going to be the highest value. And at 2, it's going to be back over here again, over here, over here, over here, over here. So this is like the sinusoidal graph over here. So we have to, be very careful about this. So let's make it. So, oh, sorry. Peak, trough, peak, trough, peak, and trough. So just to mark out the points, this is 1 point, this is 1 point, 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 and point. That's all we need to do over here. Oh, so this is 2 seconds. All right. Now, next question. State the relationship between electric field and electric potential. So basically, it's the negative electric field is the negative of potential gradient. So just to show you, obviously you can find this over here now. So going to the electric field is sorry, yeah. So state the okay. So this one, state the relationship between electric field and electric potential is the negative gradient of electric potential. Simple. So electric field is the negative gradient of electric potential. All right. Two charged isolated insulating spheres X and Y are near to each other. P is a point on the line joining the centers of spheres. Explain why it is not possible for the total electric potential and the resultant electric field to be simultaneously be zero at point P. Okay, now there are two cases over here. Now to show you with the graphs, there are two cases over here, whether the charges are oppositely charged or same charges. So this one over here. Wait, sorry, is this, wait, sorry, let me go back to the paper. Is this, oh, spheres, okay. All right. So if they're oppositely charged, the electric field never goes to zero because the electric field is in the same direction. It goes from positive to negative. So it will have a lowest point, but will never be zero. Potential, on the other hand, will go to zero. All right. But for similarly charged particles, since the direction of force is on a point between those will be opposite, so electric field will be zero at some point. But since electric field is we already described it over here, is the rate of change of potential, there will be a turning point for potential. And obviously that will not be zero, but it will just be a lowest point. All right. So we need to just describe the same thing over here. So for oppositely charged spheres, potential can be zero at a point of lowest electric field strength or electric field over here, or the weakest electric field. Okay, so over here you could also write at a point of weakest electric field. For similarly charged spheres, electric field can be zero where forces are balanced, but potential remains uh, we can say on remains on the same sign without crossing zero. Okay, now the third nail in the time. So logically it's not possible. Logically it is impossible to have opposite and same charges, same sign of charges. That's it. So since it is logically impossible to have simultaneously opposite charges and the same charges, so both quantities can never be zero at the same time. All right, the magnitudes of the charges in spheres X and Y in figure 5.1 are Q and 2Q. The spheres may be considered as a point charges at their center. So this means that we can use the Coulomb's law, the electric field strength formula, potential formula, etc. Point P is at a distance x from the center of sphere x. Electric potential at point P is zero. So when electric potential is zero, that means it's oppositely charged spheres, right? So going back, show that the distance y of the point P from the center of sphere y is equal to 2x. So we have written this definition over here, sorry, the equation over here, so we can actually use this over here. So R is basically R goes from the surface of one sphere to the surface of the other, basically. So that's what we just simply need. So they said x is the distance from the center of sphere x. So let's say this is x, and let's call it y, distance from y. So potential, remember, as k. We're saying these are opposite charges because the potential is going to zero. So k q over x. Remember, no square needed. K minus 2q over y. All right. So where electric potential is zero, that's the uh, point where um, electric field is the weakest or lowest. So we are finding the point P where at P potential is zero. Okay, now we just just rearrange. K q over x equals to k 2q over y. K and k get cancelled. Q and q also get cancelled. So we get y equals to 2x. So where y is distance from sphere y to P. Sorry, sphere capital Y to P. All right. State an expression in terms of Q, X, and the permittivity of free space in epsilon naught for the electric field strength Ex at P due to sphere X. So for this, we need K basically is 1 over 4 pi epsilon naught. So kq over r squared, so 1 over 4 pi e naught q over x squared. Simply. So, sorry, this is what we will write over here, that this is 1 over 4 pi epsilon naught times by q. Determine an expression in terms of q, x, and e naught for the resultant electric field strength E at point P due to two spheres. At point P due to two spheres. Okay, so we basically said that their magnitudes, the direction of net force is in same direction, so it will have a lowest point, but it will never be zero. So P is the point where the electric field is the lowest, but still the forces are in the same direction. So we need to find a similar expression for the sphere y also, and then add it with the electric field strength of x. So since we have Ey equals to 1 over 4 pi E naught q over y squared, but y we already said that that is equal to 2x. So this becomes, oh sorry, 1 over 4 pi e naught q over 2x whole square. So basically this means 1 over 4 pi e naught q over 4x squared. So same direction of net force. So, or like same direction of electric field, basically one direction of electric field. So E would be the sum of EX plus EY. Therefore, 1 over 4 pi E naught Q over X squared plus 1 over 4 pi E naught 2Q, we have 2Q, sorry, my bad, 2Q over 4x squared. So we add this now because 4 pi E naught is the same. We can multiply an extra 4 over here, 4 over here to make this common denominator over here. So we have 16 pi E naught x squared, 4 plus 2, 6q. So now we just simplify this a little bit. 2 times by 3, 2 times by 8. So this becomes 3 over 8. 3 by 8 q over pi epsilon naught x squared. So 3 by 8 q 8 pi e naught x squared. That's it. All right, on to the next question. State what is meant by rectification of alternating voltage. So basically, it's the conversion, simply, it is conversion, oh sorry, alternating voltage, so we can say alternating voltage to direct voltage. Alternating voltage to direct voltage. You could also see it is the conversion of alternating current to direct current. Okay, all right. State the difference between half wave rectification and full wave rectification. Okay, so we already know the answer to this, but just to show you that again, we have you covered over here. So, alternating current. See, we already have this question over here. So half wave rectification only uses one half of the AC waveform. Full wave rectification uses both halves, basically, right? So for rectification over here, we can say only one half of the wave is for full wave. Rectification, voltage in one direction is reversed, whereas for half wave rectification, voltage in one direction is removed. All right. Complete figure 6.1 to show a circuit that produces half-wave rectification of alternating input voltage. Okay, so for half-wave, we just need one diode. That's all. State the purpose of the capacitor. So basically to smooth the ripples caused by rectification. Okay. The input voltage in figure 6.1 is a square wave. Figure 6.2 shows the variation of V in with time t. All right. Figure 6.3 shows the variation of V out with t. Okay. So maximum energy stored in the capacitor is 0.41 joules. Show that the capacitance of C is 570 microfarad. Okay, so we have the change going from potential maximum, lowest, okay, because the capacitor can maximum be charged at 12 volts, and capacitance, energy is given to us over here, so we can just simply use E is equal to uh, half C V squared. So we have 0.041 electric potential energy, half C V squared is 12 squared. So C is basically 0.041 times by 2 divided by 144. So 0.041 times by 2 divided by 144. So that is this. If we convert this to the standard form, we have 5 roughly 70, 10 raised to power minus 6. So 570 microfarad. All right. Determine the resistance of R. So for the resistance, we need the time constant. So we have only like one relation between the capacitance, so RC. So C we have over here. For R, we need to figure out the time constant first. So time constant, we will actually figure out from this change in potential over change in this time. So we have V is equal to V naught e raised to power minus t over tau. So V, the 8 and 12, so 8 over 12, V over V naught, e raised to power minus t. The time that it is taken is 0.01 seconds divided by tau. So we take ln on both sides. So ln 8 over 12 equals to minus 0.01 over tau. So tau will be equal to minus 0.01. This could also be written as ln 8 minus ln 12 or ln 8 over 12, depending on what you want, minus 0.01 divided by ln 8 divided by 12. So that is this value, 2.466, 10 raised to power minus 2 seconds. So R will be tau over capacitance, 2.466, 10 raised to power minus 2 divided by 570 micro. So divided by 570 times by 10 raised to power minus 6, you get 43 basically, 43.2, so roughly 43 ohms. And that was a small question. All right, moving on to the next question. Define magnetic flux density. So magnetic flux density is coming from force over current per unit length placed perpendicular in the magnetic field. So just to show you the definition over here. Okay. Force experienced per unit length by a conductor carrying a unit current placed perpendicular to the magnetic field. So that's exactly what we just have to write. Force experienced per unit length by current by a conductor carrying a unit current placed perpendicular to magnetic field. Okay, a long straight wire carries a current into the page as shown in figure 7.1. On figure 7.1, draw four field lines to represent the magnetic field around the wire due. All right, so this is how the field lines would look like. But still, just to get a few points across so that if you encounter such a question in exam, you should be able to figure this out. So the shape of this are concentric circles. We know from the IGCSE also that the magnetic flux density or magnetic field strength decreases with as we go further. So the field lines show more separation as we go further. So field lines will show more separation with the adjacent ones as distance increases. Okay, so distance, 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 and you see the distance is increasing. Now, the final thing is the direction of the field. That is determined by right hand grip rule, where the thumb points the direction of current and the fingers, where the fingers curl, points to the direction of magnetic field. So the current is into the page. So if you use the right hand grip rule, the direction of field lines happen to be clockwise. All right. Two identical wires X and Y are placed parallel to each other. The wires both carry current into the page as shown in figure 7.2. All right. Explain why the two wires exert a magnetic force on each other. So we have already established that we are placing the wires parallel to each other. So when the wires are parallel to each other, the magnetic fields are perpendicular to the direction of the fields. Okay, sorry, direction of the currents. So we can say that both wires produce magnetic fields perpendicular to their current directions. These magnetic fields, sorry, these magnetic fields interact with each other, resulting in a magnetic force between the wires, also perpendicular to both the currents and the fields. All right. On figure 7.2, draw an arrow to show the direction of magnetic force exerted on wire X. Okay, so one thing you should remember is that when you have same direction of current, the forces are attractive. That those forces, like these wires, will try to attract each other. When you have opposite direction of current, the forces will be repulsive. So on wire X, the direction of the force will be towards wire Y. So, yeah, so I think that is enough. And they asked us to label it F. Right, okay. The current in X is double the current in Y. State how the magnetic force exerted on Y compares with the magnetic force exerted on X. So as we briefly talked about before, that these two both wires are exerting forces on each other. So attractive basically means that they both are attracting to each other. So the magnitudes of these wires will be exactly the same, but their directions will just be different. And this is due to the Newton's third law. Now, not due to the third law, this is the application of Newton's third law. Forces are applied on different objects, equal in magnitude, opposite in direction. So we just have to state, so wire on force Y, force exerted on wire Y will be same in magnitude, will have the same magnitude, we can say, as that of on X, but opposite direction. Meaning towards X. The direction of the current in both wires is now reversed. State with a reason the effect of this change on the direction of the force on the wire X. See, as we just said, if as long as they are both the currents are in the same direction, the forces will be attractive. So even if we change the direction of the currents, both of them at the same time, the forces will remain towards each other. So we will say the direction of force on X remains the same as C, the forces were produced by the interaction of magnetic fields, so both the magnetic fields are also reversed. So same as fields produced by both wires are also reversed. So are the currents. So the effect they will have on each other will be same. All right, moving on to the next question. A polished sheet of magnesium in a vacuum emits electrons when it is illuminated by ultraviolet radiation. So emission of electrons when illuminated by UV radiation, this is clearly photoelectric effect. Right. For emission of electrons to occur, the frequency of the ultraviolet radiation must be at least 8.8 10 raised to power 14 hertz. Calculate the work function energy of the magnesium. So for the work function, we need HF. So H, you can see from the data sheet or the booklet, 6.63 10 raised to power minus 34 times by 8.8 10 raised to power 14. So we have 6.63 times by 8.8 times by 10 raised to power minus 34 plus 14. We get 5.83, or just simply 5.8, 10 raised to power minus 19 joules. 5.8, 10 raised to power minus 19 joules. For ultraviolet radiation with a frequency of 11 10 raised to power 14 hertz, calculate the maximum speed of emitted electron. So how do we actually find this? This is related with the kinetic energy. So Emax is related to the HF minus the work function energy. The difference between the energy of the photon minus the work function energy. So first off, we need to find out this. 6.63 10 raised to power minus 34 times by 11 10 raised to power 14 minus 5.8 10 raised to power minus 19. Okay, so that's what we need. 6.63 10 uh, sorry, minus 34 plus 14 times by 11 mm, minus answer, we have this. This is Emax, 1.4586 10 raised to power minus 90 joules. So this is kinetic energy, so obviously half mv squared is equal to 1.4586 10 raised to power minus 19. So v squared will be 2 times by 1.4586 10 raised to power minus 19 divided by the mass of the electron. So that is 9.11 10 raised to power minus 31. So this times by 2 divided by 9.11 10 raised to power minus 31, and we get 3.2. Now we need the v, that will be the square root of this answer. So Oh, sorry, 5.65658 10 raised to power minus 5. So this is roughly 5.7 10 raised to power 5 meters per second. All right, moving forward. Frequency of the ultraviolet radiation incident on magnesium sheet is varied between 8 and 11. So between 8, okay. On figure 8.1, sketch the variation with F of the maximum kinetic energy Emax of the emitted electrons. Use the space below for working that you need. Okay, so if we look back in our calculation, we know that up until the threshold frequency, we do not have any Emax. So Emax actually starts from the 8.8. So that will be the 0 point. And at 11, we have 1.46. We can call it 10 raised to power minus 90. So this is what we have over here. So it doesn't start up until 8.8. So 8.6, 8.7, 8.8, this is where it's starting. And on 11, it goes to 1.46. So we have 0.5 divided by 10, so that is 0.05. So we need 1.46 divided by 0.05. So that is 2.9 roughly. Sorry, 29. So 1, 2, 3, and roughly 29 would be this one. So this is the rough point over here. So this is what we just need to sketch between these 2 points, from between this to this. So you can mark up these points also. So 11, sorry, 1.46, and this one is 8.80. And that's about it. All right, moving on to the next question. Fluorine 18 decays by beta plus emission with a half-life of 110 minutes. State the name of this beta plus particle. It's easy, it's positron. Show that the decay constant of fluorine 18 is this. Okay, so decay constant we find by doing ln2 over the half-life. So ln2 divided by half-life, 110 minutes converted into seconds, 60. So ln2 divided by 110 divided by further 60, you have this 1.05 10 raised to power minus 4 per second. Determine the activity of 2.1 10 raised to power minus 12 kg of fluorine 18. Okay, so for that we need the number of nuclei in this. So the number of nuclei in this we can find out by doing mass divided by the molar mass. That will give us the number of moles times by the Avogadro's constant, right? So we have 1.05 10 raised to power minus 4 times by mass is, this is in kg, so we will have to times by 1000. So this becomes minus 12 plus 3, 9, divided by the molar mass of fluorine 18, that would be just in grams 18, times by 6.02 10 raised to power 23. So this is what we just need over here. So 1.05 times by 2.1 times by 6.02 divided by 18 times by 10 raised to power minus 4 minus 9 plus 23 we get this value 7.37, 10 raised to power 9, and this could be simplified to 7.4, 10 raised to power 9 becquerels. A small sample of fluorine-18 is injected into the body, acts as a tracer for use in medical imaging. Describe how the interaction of the beta plus particle with an electron in the body enables the formation of an image. So this is an easy thing to describe. So we can say that the electron and positron annihilate upon interaction, converting their combined mass into electromagnetic energy in the form of two gamma photons traveling in opposite directions. Okay, now this is like 2 points combined into one, like how they annihilate, they convert their combined mass into energy, which is in the form of two gamma photons traveling in opposite directions. Now, the time difference between arrivals of these photons at the detector is used to uh, pinpoint the location of annihilation, creating an image from multiple events, like multiple annihilation events. Okay. Suggest why 110 minutes is a suitable half-life for a nuclide used as a tracer in medical diagnosis. Now you can find the answer for this in the FAQs also. So we can say that this is this half-life is long enough for imaging or testing, uh, imaging or scanning, sorry. So imaging or scanning, and short enough to decay completely within a few hours, preventing unnecessary radiation exposure to the patient. Okay, all right. All right. Question number 10. Explain how the redshift leads to the idea that the universe is expanding. Again, you can find this answer in the FAQs over here, but let's explain this. So basically, what redshift tells us is this basically. If there is redshift, that means the object is going. So, for example, if this is Earth, the object over here, let's say, is a galaxy over here. So, galaxy is moving away from us. This is what redshift is telling us. And then, if we combine the data of the galaxies and stars from all around us, and we arrive at the same conclusion that all of the wavelengths that we're receiving are redshifted, all of these objects are moving away, that means the entire universe is expanding. So first off, we might have to describe a little bit of a redshift. So Doppler effect causes an increase in apparent wavelength uh, observed due to light source receding from observer, causing redshift. Okay, now the wavelengths from distant galaxies, stars, is observed to be redshifted okay now distant galaxies is observed to be redshifted when this redshift is observed from all around observer Earth, it can be concluded that the universe is expanding. Okay, so we have to be very clear about the reasoning over here. So what is redshift? So it's the Doppler effect that's causing the observed wavelength to be slightly higher than the original one. And when we are observing the wavelengths from distant galaxies, it is observed to be redshifted. And when this observation is done or happening from all around the Earth, observed from all around the Earth, from distant corners of the universe, you could also say from all around universe, space, it can be concluded that the universe is expanding. All right, stars in a distant galaxy emit radiation. The total luminosity of the stars in the galaxy is this. Oh, sorry. The emission spectrum of the radiation contains a line X at a wavelength of 658 nanometers. Okay, the radiation from the galaxy is observed on Earth. The observed radiation has a flux intensity at this. In the observed emission spectrum, the line X is at a wavelength of 726 nanometers. Okay, determine the distance d from the of the galaxy from the Earth. So we can do that from the flux density. So flux radiant intensity, sorry, luminosity over 4 pi d squared. So d squared is basically L over F times by 4 pi. So luminosity is given 1.9010 raised to power 36 divided by flux radiant intensity 8.42 10 raised to power minus 16 times by 4 pi. This will give us the d squared. So 1.90 divided by 8.42 divided by 4 pi times by, now the powers of 10, 36 plus 16, we get this value 1.795 10 raised to power 50. So therefore d will be the square root of this value. It's 1.34 10 raised to power 25. Now over here we're using three significant figures because as you can see three significant figures over here. So three significant figures because the data we have are all of them in three significant figures. So that's why we are having three significant figures over here. All right, sorry, 1.34 10 raised to power 25. Okay, speed v of the galaxy relative to the Earth. So we can find this using the redshift. So change in wavelength over the original wavelength or true wavelength at stationary wavelength from a stationary source, v over c. So v will be, sorry, v will be just simply delta lambda over lambda. Sorry, it's the other way around. So lambda times by c. So 726 minus 658, right? 658 times by 310 raised to power 8. So 726 minus 658 divided by 658 times by 310 raised to power 8. So 3.10 10 raised to power 7. 3.10 10 raised to power 7. Observations of many galaxies, such as the one in B, lead to many pairs of values of D and V. Plotting these values reveals a trend. Sketch the variation of V with D. Now, this is basically the Hubble's law. Okay, so Hubble's law is V is equal to H naught over D, which means a constant gradient and a direct proportionality. So this line is actually passing through the origin. State the name of the quantity represented by the gradient of the line. This is just the Hubble's constant. And that's your paper. All right. So if you feel that I have made a mistake somewhere or you would like some clarification on something, reach out to us, please comment and go through the resources that we have put together, buy them from the Patreon and comment on how you find them. If there's any improvement needed, if there's any mistake you spot, we will send you a free copy of that too. All right, so see you in the next video. Bye bye.